All right, so on the top of page 99, if we check our derivatives, oh, boomer. Sorry, my cat bit me while I'm making this video. We should have 2 to the power of x squared times the natural log of 2. But then we've got to remember the chain rule, which means we need to multiply that with 2x. And like, to be honest, I don't know what order we would end up writing those factors in, but if a question showed up on a multiple choice test where that was a solution, we would just look for something that resembled that solution. All right, for our next example, we've got 4 to the power of the sine of x. So we've got an exponential base 4 where the junk, so to speak, is the sine of x. So 4 to the junk times the natural log base 4 times the derivative of the junk. So the derivative of the sine of x is the cosine of x. All right, the next one, we're switching gears to integrating now. And when I look at this next example, I notice that we have a quadratic x squared in the exponent, and I notice we have a linear x. And that, to me, because we don't have a product rule for taking integrals or antiderivatives, that usually is a good indicator that we might need to do a u substitution here. So let's let u be x squared so that du could be 2x dx. So if I think about it, I need to create a 2 on the inside of my integral, which means I need a 1/2 on the outside. So we might just rewrite our integral like that. Okay, so now we can see that u is x squared and that du is the 2x dx piece. Here, du. So when we go to perform that u sub, that 1/2 out front comes along for the ride. We keep our integral symbol. The 2x and the dx, they don't go away, but that's what becomes du. We're left with the base 3 of the exponent to the power of u du. Okay, so now this is just like one of our general integration rules that's in the box, that when we integrate an exponential with a base other than e, the natural base, we get that exponential divided by the natural log of the base. So when we integrate this, we're going to have 1/2 times, well, 3 to the power of u divided by the natural log of 3. And then let's not forget our plus c, because that is an indefinite integral, so we cannot forget the constant of integration. To complete this, since we're not evaluating the integral, we need to go back and rewrite it in terms of x. So that is 3 to the power of x squared, again, all of that over the natural log of 3 plus c. And then we could explore some ways to rewrite that, because we could write that as 3 to the power of x squared over 2 ln of 3 plus c. Or, interestingly, we might rewrite that as 3 to the power of x squared over the natural log of 3 squared, which is 9. So don't forget, when we multiply our log function by a constant, that constant could become the exponent of the argument of the logarithm. So we could have that plus c. Moving on to that next integral, so we have secant squared x times 4 to the power of the tangent of x dx. So that complicated product is our integrand. And again, when I see something this complicated in our integrand, it jumps out at me that this might be another opportunity to try a u substitution. So if we think, what is our innermost function? Well, we have an exponential function that the innermost function, so it's composed of the tangent of x. So what if we tried to let u be the tangent of x, which means that du would be the derivative of the tangent of x, which is the secant squared of x dx. So if we complete this u substitution, all of this is our u, and then all of this is our du. So we're really just left with 4 to the power of u when we rewrite this. Well, 4 to the power of u du. Okay, so if we use the rule to find the antiderivative, it's going to be 4 to the power of u divided by the natural log of 4 plus c, because it's an indefinite integral. And then we know that we want to go back and resubstitute the tangent of x for u. So 4 to the power of the tangent of x over the natural log of 4 plus c. Final answer there. All right, lastly, we've got some derivatives of logarithms where it's a log base, not e, so not the natural base. So let's look at these. The first one's a pretty straightforward application of that general rule. So if I take the derivative of log base 2 of x, I'm going to get 1 over x times the natural log of 2. And again, like if we're unsure, we could prove that using logarithmic differentiation, but it's kind of gross to do that. It's a lot of work. The last log function, so we've got log base 10. Recall from algebra 2 that we call log base 10 the common logarithm. So log base 10 of just any function x is the same as just log of x. So in this example where we don't see a base, that really has the base of 10. So if we rewrite this, we've really got log base 10 of x squared plus x, and that's what we wish to take the derivative of. We could use our properties of logarithms to, actually, never mind. No, we couldn't. My first thinking was we could rewrite that as a product. We can, like we could factor a greatest common factor from x squared plus x. But as I think that through, I'm not sure that's really necessary. So let's just use our property. So we're taking the derivative of log base 10 of some junk. So we're going to use that rule. That's going to be 1 over, now in the past we said it's 1 over x, but now we've got this junk here instead of the x. So we get 1 over x squared plus x times the natural log of 10, because that was base 10. But because we're taking the derivative of log base 10 of some junk, we have to multiply by the derivative of the junk. So we end up with 2x plus 1 over x squared plus x times the natural log of 10. So the way I was thinking about that would actually be more complicated, and there's probably no reason to do it the harder way. So that's just what we get when we do it that way. All right, that was our last example for section 7.2. These properties are kind of challenging, but honestly, I would just recommend memorizing the 3 new general properties that are in that box and just trying some of the practice problems from this section.